Hey guys, welcome back. In this video, in this lesson, we're going to just extend the use of finding integrals by hand to finding solutions, okay? So the first thing we're going to look at is how to find the general solution to the differential equation. All right, so what makes it a differential equation is that, one, it's an equation, but it's got something like dy over dx equals, all right, something with x's in it, okay? Now, when you solve a differential equation, the first thing you have to do is separate the variables, okay? Now, what that means is that anything with a y needs to stay on one side, and anything with an x needs to go on the other side, okay? So you need your variables on opposite sides. And that is now called a differential. And once you separate your variables, you are ready to integrate both sides, okay? Integrate both sides, because now it's an equation. The integrals we did earlier were just the integral of a polynomial or something like that, but now we have an equation, so we're going to integrate both sides. And when we integrate on the left, it's like integrating a 1, right, and the variable is a y, though, okay? So when you integrate a 1, you go back to the variable, normally x, but because this is a dy, we go back to y, okay? And then on the other side, we're going to apply our new power rule. So we're going to keep the coefficient, and then we're going to add a power and divide by the new power, and then we're going to add c. And last but not least, we're just going to do a little bit of simplifying. 3 and negative 3 can reduce to be negative 1. The x needs to go to the bottom, and then we have our plus c. And that is the general solution, okay? It's a general solution because it represents a lot of solutions to this differential equation, because c could be any constant, a positive number added, a negative number added. And so it basically represents a family of solutions where c could be any number. So that's why we call it the general solution, okay? Now, the next part we're going to look at is finding the particular solution. And what that does is you have to be given a little bit more information, but that will allow you to actually solve for c. You will actually be able to find c. So we're going to find the particular solution to the differential equation. Okay. So again, you need to be given a differential equation. For example, let's see, this is our second problem. Let's write it as f prime of x this time, okay, equals 9x squared plus x minus 8. And then I'm going to give you a little bit more information. I'm going to tell you that f of negative 1 equals 1. And that's what you're going to need to help you when you get to the finding c part. Okay, now technically we don't integrate in this form because f prime of x doesn't actually have a dx attached to it. So when you're being really formal about it, you really should change this to dy over dx. Then you can move your dx over, because there has to be one in order for you to integrate. All right, so we have to separate our variables, and then we can show that we are integrating, okay? And once we integrate, all right, we're going to get y equals, and we're going to apply some power rules. So add a power, divide by the new power, add a power, divide by the new power, And you can think of it as adding a power, or because it's a constant, you need a variable. And then, of course, plus c. All right. Now, what you have to understand is that y is essentially your f of x. Okay, right? Because we started with f prime, so now that's your f of x. And then we're going to do a little reducing. And I prefer fractions, but you don't have to do that. All right, so now we've got our general solution. Well, we were given another piece of information. We were told that f of negative 1 is 1. So what that means is, if I plug in negative 1 for x, it should equal positive 1. And I can use that information to solve for c. Okay, so let's see. This is going to give me negative 1 times 3. This is going to give me positive 1 times a half. This is going to give me positive 8. All right, and so that's going to give me 5 plus a half. 5 and a half is 11 halves plus c. And then 1 minus 11 halves is negative 9 halves. Okay, and then once I have my c, I can officially write my particular solution. Well, how do I do that? Well, I'm going to look at my general solution and pretty much copy it down, except instead of putting plus c at the end, I'm literally going to put the answer I got for c. So I'm going to put minus 9 halves, and that is what we call a particular solution. Okay? All right, that is our particular solution. So we have solved the differential equation, and we were given information to help us actually find the c. Okay, so I've just got several more examples for us to look at, so you have lots to go on when it comes to practicing on your own. All right, so my next one is a little bit different because I'm starting you with the second derivative. Okay. And then I'm going to give you a couple of pieces of information. Whoop, that one doesn't have a prime on it. Again, get it together here. All right, and so when I want the particular solution to this differential equation, that means go all the way back to f of x. So we have a second derivative, and we have to work our way all the way back to the original. So we're actually going to have to integrate twice. Okay? All right, so let's remember our notation for the second derivative as a differential. Looks like this. All right, and again, it's just notation, but you still need to separate the variables. Okay, just understand you're still only going to integrate this polynomial here. I mean this x raised to a power. Sorry, it's not really a polynomial. All right, so when we integrate, all right, when you integrate the second derivative, it's going to take you back to the first derivative. Okay, now technically, I guess we should do it like this. This side takes you back to dy. And then we integrate this like a normal power rule. So we add a power, divide by the new power, I'm going to multiply by the reciprocal. And then technically this dx squared, right, the second derivative of x, turns into dx. But you really want it over here when you're done. So technically it starts out here, but we divide it over here. All right, and now the proper notation for that to match the given problem is that that represents the first derivative. All right, and then of course you need your plus c. All right, and I'm going to change that exponent to positive and change it back to a square root because that's probably going to make it easier for me to solve for c. Okay, so then I take the given information for the first derivative, f prime of 4 equals 2. So that's telling me if I plug in 4 for x, I should equal 2. All right, and so square root of 4 is 2, negative 2 divided by 2 is 1, negative 1. And when I get c by itself, I get 3. Okay, so my first derivative solution is negative 2 over the square root of x plus 3. Okay, now I need to basically start over. Okay, I need to start over. So I'm going to take a second and I'm going to write that down again. All right, and remember this represents dy over dx. I'm going to change this back to a negative exponent to make it easier to integrate. And I'm going to take a little bit of a shortcut. And I'm going to go ahead and just make this dy and make this times dx. Okay? And then I'm going to show that I am, in fact, integrating both sides. Okay, so I've separated my variables, and then I'm going to integrate both sides. So on the left, I get y. And on the right, let's see, keep my negative 2, add a power, so I get a positive 1/2, so I'm going to multiply by another 2. I need an x with that one and a plus c. And some of you may be asking, why don't we add c to both sides? And because a constant, it's not this, it wouldn't be the same constant added to both sides. And so it's like saying, well, let's just move it all to the right. You're still adding a constant, okay? All right, and then just for notation purposes, I'm going to change this back to f of x. I'm going to do a little simplifying. And then I can plug in the other piece of information that says if x is 0, then it should equal 0. And that actually gives me c equals 0. So last but not least, I'm going to take one more step to actually write the solution with the 0 plugged in for c. Okay, so it is not a particular solution if you still have plus c on the answer. All right, now I want to do one with trig as a good refresher. So let's take a look at, I'm going to give you that the second derivative is equal to sine of x. And I'm going to tell you f prime of 0 equals 1 and f of 0 equals 6. Okay? So the first thing I'm going to do is separate my variables by moving all of the x's to the same side. By the way, when you do this for a free response question on the AP exam, if you do not show them that you move the dx over, you are ineligible to earn any points. Okay, so you always have to show that step, right? Then we are going to integrate. All right, and I'm gonna go ahead and put my dx, because I know I'm gonna end up moving it back to make it dy over dx. And then I just have to remember the integral of sine. The integral of sine is negative cosine of x plus c. And then as long as you understand that this represents f prime of x, I'm going to plug in 0 for x. And according to this, it is equal to 1. And then I can solve for c. Well, cosine of 0 is 1, but there's a negative in front of that. And then when I get c by itself, I get 2. All right, so my first solution here is negative cosine of x plus 2. And then I'm going to start the process over. I'm going to separate my variables, understanding that the whole thing on the right is multiplied by dx. And then I can integrate y equals, well, then I have to remember what is the integral of negative cosine of x, and that is negative sine of x. The integral of 2 is 2x, and then I need to add c again. And then I find the new c. Well, f of 0 is 6, so that means when I plug in 0 for x, this thing should equal 6. Well, sine of 0 is 0. 2 times 0 is 0. So C ends up equaling 6. And last but not least, and it really doesn't matter if you leave it as y equals or change it to f of x, because basically the information given to you was in both forms, so you pick one, and then you just need to finish by plugging in C. Okay? All right, now, let's think of an application type problem of when we might be asked to perhaps go from the second derivative back to the original. And that comes up when you have one of your motion problems, where you have like acceleration and velocity and position and all that stuff. So that's the next problem that we're going to do. We're going to do an application problem, a motion problem, but I'm actually going to pause the video while I write the problem down, because that'll take me a second or a minute. All right. All right, so here's our problem. A particle moves along the x-axis, so its acceleration at any time t, where t is greater than 0, okay, so positive time, right, is given by a of t equals 5 minus 2t. When t equals 0, the velocity is 2, and its position along the x-axis is the origin. And the question says find the velocity v of t in terms of t. So that literally means find a function for velocity, right? And so what does that mean for us? Well, we're starting with acceleration, and we have to remember how to get to velocity, right? Well, you integrate. But before you do that, you do want to, you can kind of shortcut it a little bit, but you do need to show that you technically have a dt over here before you integrate. And when you integrate velocity, acceleration, you do in fact get velocity. All right, and then when you integrate a constant, you get the constant times the variable. Whoops, not x, I need t. Okay, and then of course for the other piece, we're going to apply a power rule. But when we divide by the new power, the 2's should cancel out. Now, if you need to show that step, that's fine. And then, of course, you need a plus c. Well, technically, that is not velocity in terms of only t, because you haven't actually found the constant. Okay, so you don't have the full velocity function without finding the constant. Well, that's where the other information they gave you comes in. It says when t equals 0, the velocity is 2. So what they're really saying is that velocity at 0, v of 0, is 2. And then it says, and its position, well, remember, sometimes we call position x of t. And so that's what I'm going to call it here. And so that's saying x at the position at time 0, right, is at the origin, which is also 0. Okay? All right, so v of 0, so we're going to plug in 0 for t. And you don't have to show this technically, but you do have to show that c does in fact equal 2. And then you have a velocity function. Okay, so you go back and just plug in c. All right, so there's your velocity function. That's the answer to this first part. Now, the next question I'm going to ask you, and just so I don't have to scroll down, I want us to find the position function, and I'm going to call it x of t in terms of t. All right, so what does that mean? That means I'm going to start with the velocity function I just had. Okay, I'm going to technically set it up correctly by putting a dt out here before I integrate. Okay, and when I integrate velocity, all right, that takes us back to position. And then let's see, we need to apply a power rule. So when I divide by 2, it's just going to stay 5 over 2. Add a power, divide by the new power, makes this a 1/3. Don't forget to throw your t there and then your constant. All right, but then what do we know about position? Well, we know at time 0, the position is 0. So I should be able to plug in 0 for all of these t's and set it equal to 0 to solve for C. And so last but not least, I just need to take the time to rewrite the function with that 0 plugged in, or in other words, left off. Okay, so there is your position function. And remember, over here, we were finding the velocity function. All right, and so now that you know how to find those by hand, you may also be asked to do things with them. So you can't forget what you can do with velocity and acceleration and position and so on. Because now we know how to integrate them by hand, and so now it might not be on a calculator question, okay? And that concludes our lesson on finding solution.